So this is going to be a quick introduction to YSOVAR for my LLAMMa CephC team. So we've already talked about this cartoon in the context of how stars form, at least low mass stars form. So if you don't remember the details of this cartoon, you should go watch that other star formation movie. This is how professionals show that same concept. And I can't remember if I went through this in detail in the other video, but let me go through it briefly here. So in this column, we have a cartoon where you're going from something inside a cocoon to something that's sort of dispersing like a cocoon, still having a big disk, dispersing the disk and forming planets. Over here on the right-hand side, you have something called a spectral energy distribution, where you have energy as a function of wavelength, both log scale, and that is a black body. It is a cold black body. So for the most embedded things, any energy given off by that central object as it's condensing is masked, is enrobed, is reprocessed by the cocoon of matter around it. So it looks to those of us outside like a cold black body where the peak is at 20 microns or so. Okay. Now, a little bit older, you've dispersed some of the cocoon, you have more central mass, you have a big disk, but you also have remnants of the cocoon. So in this spectral energy distribution, this component here, this warm black body here, is representative of the emissions coming from the central source. But you get a lot more energy out in the longer wavelengths because you still have a lot of dust around the central source. So that dust is still intercepting and reprocessing the radiation from that central object and creating a lot of infrared excess. So here, most of the energy is coming out in the infrared. This divot here is actually a very, very broad absorption line. It comes from silicates. It's called the 10 micron feature, and it's basically sand that's in this dust. And it creates an absorption line here that looks like a divot out of the shape. But you can also think of this net SED as the sum of two black bodies, one warm one from the central source, and then a cooler one. You can kind of see that here. It doesn't exactly work because the intensities of the two components are very different, but the basic idea is that you have most of the energy coming out from the dust that's around the source. Eventually, the envelope thins out, you have a disk. Now, most of the energy is coming from that central source, where, again, the dashed line is the component from that central object, the stellar black body curve there, and then you end up with a little bit of an infrared excess from the disk because you don't have as much dust around it. And then a little bit older, the disk is more dispersed. Almost all the energy is coming from the central source. Depending on how much dust you might have a tiny bit of excess in the infrared from that dust. So astronomers call these earliest phases class 0. It's probably when most of the matter is accreted onto the central source. The envelope is still pretty substantial, and this lifetime is very short. The details are unknown, maybe on the order of 10 to the 4 years, so 10,000 years. Class 1, a little bit older, still accreting, but not as much. The envelope is much less massive than it was before. This lifetime is a little bit longer than class 0, maybe 10 to the 5th years. Class 2 still have a disk. The disk is not very massive compared to the central source, and this lifetime is maybe 1 million years. Class 3 is when you have an optically thin disk, and the disk is very much less massive than it was before, and this lifetime is maybe 10 to the 7 years, so 10 million years. There's a lot of uncertainty in some of those ages, and there's a lot of nightmares of nomenclature because as people have collected more and more of these objects, they've had to invent more and more terminology to explain them. So this original series of classes was entirely empirically defined by the spectral energy distribution as observed. And here you have a rising SED. Here you have a falling SED in the infrared. And so necessarily in between this and this, you must have some that are more or less flat. So those that are in the middle there are sometimes called flat class. These with big thick disks are sometimes called classical T-Tauri because the prototype T-Tauri itself has a disk like this, and so it became the name for the entire class of objects, and so class 2s are sometimes called CTTSs or classical T-Tauris. Then in between having a big primordial disk and forming planets, you have to go through a transition where the dust is no longer primordial. It may be a result, it's trying to disperse itself in some fashion, whether it's all evenly or inside out is not so clear, but you have transition disks in the middle. And then as you disperse more and more of the dust, you might have second generation dust from collisions of the planetesimals. So you end up with debris disks there. Nomenclature really is sticky, and you have to be really clear when you are talking to people and writing about it that you are very precise in what you mean by what classes. So in the context of YSOVAR, we're calling everything here that's young a young stellar object. So YSOs. And YSOs are young, usually with higher excess emission, not all the time. Most of what we're going to have is class 1s and class 2s because we're primarily using infrared to find them. We're going to find some class 3s because we have X-ray data as well. And in NGC 1333, there were some class 0s that we could investigate as well, but I don't believe there's going to be any in CephC. There'll probably mostly be class 1s and 2s with some class 3s. As the late, great Tal Maliazzi was quoted as saying, reality often astonishes theory, and that happens a lot in astrophysics. So specifically in the context of SED classes. This is the first of several slides with caveats. So the story that I've woven with the cartoons and the movies from the other video and the cartoon that I just showed you with the SEDs, it seems very well defined. But there's an awful lot of details that have gotten swept under the rug here. Technically, this process only applies to low mass stars. High mass stars probably do this just faster. We don't know. Lower mass stars like brown dwarfs probably do this too, only slower. The classification, the original placement in the class 0, 1, 2, and 3 is based entirely on the empirical spectral energy distribution as observed. That physical interpretation that says, okay, the SED is shaped like this, therefore I'm going to interpret that as that amount of infrared access as degree of embeddedness is an additional step, okay? So class 0s being the youngest and class 3s having freed themselves and being the oldest is a separate step from the observed shape of the spectral energy distribution. That link between the shape of the SED to the interpretation of it as dust to then an implicit association with age is a separate logical steps for all of those. Class 2s and 3s are found at about the same ages. And so that was very confusing for a long time. It's still very confusing. Some stars seem to lose their disks very quickly and some do not, and no one really knows why. We don't really have enough age determinations for the class 0s and 1s because they're so hard to get an age for. People are still working on this, but probably we're finding some of these at the same place in the same time. In other words, they're too close together to be formed separately. And so there's a clump of objects in the star formation cloud Perseus that I found that has everything from pre-class 0 all the way to class 3 within a very tiny region of space. And it's not clear how you do that, especially if you really want to interpret the SED shape as age. How are they doing that? How are they getting rid of their dust so spectacularly quickly in some cases and so slowly in others? There's another thing that's sort of informally called transition disk wars. So there's basically two camps in the community. There are people who think that older disks disperse steadily, evenly, isotropically. In other words, at all radii from the star, it steadily goes down in amount of dust. Or it could be that they disperse from the inside out. In other words, you start out with a small hole around the star and eventually you get a ring with a big hole inside it. It's totally unclear who's right at this point. And it's also unclear what kinds of structure, or you might think of it as texture, can be found in the disks and how that relates to planet formation and what is driving that structure and how that connects to planet formation. It's completely unknown. But looking at the time domain, like YSOVAR does, can help clarify what kinds of structures there are in these disks. Inclination matters. So you can imagine that if you have an edge-on class 3. So you have not a lot of dust, but you're seeing that central object through all the dust that it's got. So the observed SED may end up looking like a class 2, even though it really is closer to a class 3. And that may be the answer to the question of how you get class 2s and 3s are at the same age. But that's not necessarily the only thing that's happening. So the inclination does matter, but the details of it are not yet clear. The accretion rate matters. So stars may be accreting little bits of matter continuously, or it might be accreting a whole bunch at once. It could be that the magnetic field creates basically a trap for matter moving through the disk, and it holds it like a dam until it gets enough matter, and then it catastrophically dumps a whole bunch of stuff on the star. So if you do that, the models that we have say that things are really confusing when that happens, because you end up with the star puffing up, and it's really hard even in the model to tell what's disk and what's star. It's very confusing. And if you happen to catch something that's in the middle of one of these, fantastic accretion rate objects, it may look to us more embedded than it would, a year earlier if we saw it at lower accretion rates. And the timescales for this, the fraction of stars that could be doing this, is just not clear yet. But the time domain can help with this too, because we're trying to understand how accretion works. At the end of the day, most people, when they say class 0, 1, flat 2, 3, they mean that that's an age sequence from youngest to oldest. But you have to keep in the back of your mind that there's a lot of uncertainties in interpreting the SED classes this way. So this, I'm pretty sure I showed you before. This is my super crappy PowerPoint picture of a young low mass star. It is not to scale. You note that I've got the arrows there. This is a class 2, so it doesn't have jets or a cocoon anymore. It has a big honking disk still, though. So you've got this young star that's in the center, and because it's low mass and still condensing out of the main sequence, it is entirely convective. Because it is rapidly rotating and entirely convective, it has big honking spots. Now, sunspots on the sun, even when the sun is at its most active, occupy only a few % of the star's face. But for these young stars, you could have spots occupying more than half of the star's face, because they're incredibly active young stars, and they could have very long-lived spots that are very, very large. And so you end up with these giant star spots from stellar activity. But then because you have these big disks too, you have the magnetic field, the strong magnetic field from these young, fully convective stars that are rotating quickly. You end up with the strong magnetic field from that. And that magnetic field is so strong that it threads the disk and actually truncates the disk before it gets to the star, and you end up with matter that crawls up the accretion columns and crashes down onto the star. And when it does that, it creates a shock, a ring, an arc, a spot where that stuff is hitting the star. So all of these things together mean that you've got a lot of variability. You've got the spots are creating flares, and so you're going to produce X-rays that are variable, as well as H-alpha from the flares. The accretion columns are going to emit lots of emission lines, including H-alpha, sort of screaming on its way into the star. The shock is going to create an ultraviolet excess, so more UV than you expect from a plain star if it's actively accreting. And the disk is going to create infrared. Close in is going to be near IR, and just, IR in general, and then further out is going to be mid-IR, further out, far IR. You also can get scattered light if the disk is flared, as it's shown here, which then just really complicates your models of the spectral energy distribution. This is what a real artist can do with that same mental model. So here we have the young star with magnetic fields threading the disk and actually truncating the disk. And you can see in this particular case, this came from a press release that I had where it was trying to explain why some stars rotate slowly and some stars rotate quickly as a result of so-called disk locking. When you have the magnetic field threading the disk, the star is trying to spin up because it's contracting on the main sequence like a skater pulling in her arms, spinning faster and faster and faster. The star is trying to spin faster and faster, but it's got to drag the magnetic field along with it, and it's trying to drag the magnetic field through the disk. And if the disk has enough charge to it, or it is dense enough that the charged particles can't move quickly through the neutral gas and dust, then you end up with so-called disk locking, where the disk actually locks the rotation of the star to that of the disk at the lock point. So it's really complex stuff. This may be what a real disk looks like, where there's clouds and texture and arcs of dust that poke up above the surface of the disk and, in this case, temporarily occult the central source. Now, those were both artist concepts. This is real data. This is a jet called HH30, and you can see here, this is HST data, you can see here that it's got a nearly edge-on disk that flares, and it's got a jet. So you can see stuff moving out through the jet with time. These frames are about 1 frame per year. And you can see in that bowl that we're barely able to see into on that top hemisphere there, you can see that there's a bright region. And probably what that is scattered light, reflected light, basically, coming from a hot spot on the surface of the star as it's rotating around. So you can see it's incredibly complex. This is also real data. This is real data also from HST, but this is in a different region. This has the relatively unpoetic name of that. It's in IC 348. Here you have, again, so this is a lot further away than HH30, which is in Taurus. HH30, the previous thing, is only about 140 parsecs away. This one is further. You can see there's probably an edge on disk here. And you can see that intermittently this whole region brightens. And then you end up with sort of an echo moving out through a cone here, as well as down here. So the way that these folks interpret these observations is that you have a binary on a very elliptical orbit. And when the stars come closest to each other, periastron, you end up with this brightening, and then they fade again as the stars move further away to periastron. And so you end up with this periodic substantial brightening of this system. So one thing that you should remember is that the young star environment is incredibly dynamic. It is changing all the time. Back in the 40s and 50s, when people were still trying to figure out that stars were young in the first place, originally optical variability was one of the defining characteristics for finding young stars. And perhaps as a result of that, much of the literature, young star monitoring to date, has been in the optical. But it turns out they also vary in X-rays and in radio and in the ultraviolet. And it turns out they vary in the infrared too. We weren't entirely sure that they were going to do this, that they were going to vary in the infrared. In fact, there were some people that were arguing there's no way that they could vary in the infrared, except they do. And Spitzer really put a nail in that coffin. There was some early, very, very difficult work done trying to establish that young stars really do vary in the infrared. So this is just the laundry list of people trying to figure out how and if young stars vary. So in many cases, they're trying to compare ground with space-based observations. And it's sort of serendipitously uncovered variability where they're trying to combine observations from multiple facilities and concluding, wait a minute, this is not the same brightness. It has changed a lot. So very early on, it was really tough to make reliable assertions that these stars were varying in the infrared. The first space-based campaign to monitor in the infrared that I know of was in 2007 with a European mission called ISO, and they were deliberately monitoring them from space in the infrared and from the ground in the optical, and they found some variability. So just to remind you, when you're looking at these longer infrared wavelengths, you can be looking quite a ways out from the star. So at 2 microns, which is K-band, which is where a lot of monitoring in the infrared is taking place, you could be, 10 stellar radii out. By the time you get to IRAC 1 and 2, it could be 50 stellar radii out. So the IRAC 1 and 2 monitoring, which is what we did, is going to be sensitive to disks that are further out or texture further out than you find in K-band. But in reality, this is just a back of the envelope, back of the napkin calculation. It's not even remotely this simple in reality. But we do need to figure out what exactly is it that's varying in the infrared, and what timescales is it varying, and is the thing that we're looking at really tens of our star away from the star, or is it really much more close in? So we use Spitzer. Spitzer is an 85 centimeter telescope, so not that big. The telescope is in here. The light comes in this way. The instruments live here. The cryogen, when we had it, lived there. And this is what the engineers call the spacecraft. It's electronics, communications, all that good stuff. There were 2 science cameras aboard, IRAC and MIPS, and a low to moderate resolution spectrograph called IRS. We monitored mostly with IRAC during cryo, just a little bit. Some MIPS monitoring was done too. It was launched in 2003. It's in the Earth trailing solar orbit, which makes it, something like 15 light minutes away one direction, and it is hugely more sensitive than the prior all-sky survey that was available. Now, this is one of the first images released from Spitzer right at the beginning of Spitzer's mission. And it turns out that we decided to go look at the same region to look for variability, in part because of the mechanics of what the telescope can observe when. And lo and behold, we found that the young stars vary. So Maria Morales Calderon led a study where we were monitoring for the first time young stars in all 4 of the IRAC bands, which is 3.5, 4.5, 5.8, and 8 microns. We monitored twice a day for 2 weeks, and then for a 7-hour chunk in the middle, we monitored every 12 seconds. So more than half of the young stars there were variable on a variety of timescales, which led us into some physical interpretations. There are some cases that we thought were spots, sometimes spots illuminating the inner wall of the disk, sometimes flares, sometimes intermittent accretion. M-dot is DMDT, or accretion rate, disk shadowing, or spots. So in general, we found that larger amplitude variables are more embedded, which could mean that they are younger. We also found a young Delta Scuti star, which means that we found it pulsating on top of rotating, which is really cool. So these are just some of the light curves. Here's brightness in magnitudes as a function of day. And the 2 points, the 2 colors in points, are the 2 channels. So you can see that these young stars really are varying in the infrared. When we ran out of cryogen on Spitzer, we still could operate the shortest 2 channels of IRAC at 3.5 and 4.5 microns, and it's super efficient. We have funds through fiscal year 16. We're going back to the senior review to get funds to see if we can keep going. But the critical thing here is that it is phenomenal for monitoring anything, but particularly young stars, because it's super stable, super sensitive. It has a relatively wide field of view. A lot of ground-based monitoring programs have to deal with the fact that the sun comes up every day, so it's very difficult to get continuous long cadence observations, but from space you don't have that kind of issue. And at 3.5 and 4.5 microns, we're sensitive to both the photospheres from the young stars as well as the dust. And moreover, Spitzer is super efficient. So there are 7,000 to 8,000 hours per year of science to be done with Spitzer. And so we have a very large program called YSOVAR. Some people think that it's called YSOVAR, as in why are you so variable? It really is YSOVAR because it means young stellar object variability. It consists of 2 very large and several small Spitzer guest observer programs. It really is the first sensitive, wide area, mid-infrared, time series monitoring of these young stars on time scales of hours and minutes to years. It includes 1 square degree of the Orion Nebula cluster, plus embedded regions for 11 other star-forming regions, including simultaneous monitoring with a space-based optical telescope in NGC 2264. So in the end, we have more than 800 hours of Spitzer time monitoring young stars. Now remember, I said that we have 7,000 or 8,000 hours per year available of Spitzer time. So even though we got these observations over several years, remember that about 800 hours is 10% of the time on Spitzer, and we're using it to monitor young stars. Typically, we have about 100 epochs per region, where we're going back about 2 or 3 times per day for about 40 days. We sample much less frequently for longer time scales. In the end, we have 39,000 light curves that represent unique light curves from 29,000 objects. And in the end, we have a couple thousand young stars that have really good light curves. The data have been taken over the period between September 2009 and January 2014. So at this point, we're trying to chew through it. I don't know exactly what we thought we were getting into when we wrote these proposals. I think we thought it was going to be like this. I mean, we had been through the commissioning of Spitzer. We knew how tough it was. We knew how fast the data were going to come in. And we thought, okay, we're just going to be able to handle it. And we're going to, try to pick off the easiest things to do. Instead, it was really much more of this kind of an experience where the data it was overwhelming. We had so much, so fast, from space and from ground, and just managing it all was a serious, serious challenge. But we're getting there. So John Stauffer is the PI. I'm the deputy of this program. The two postdocs who've done the lion's share of the work are Anne Marie Cody and Maria Morales Calderon. And there are many, many others and more folks affiliated with the programs. We do have a website, even if it's not updated super frequently. Our science goals are to probe physical structures on the small spatial scales that we can identify through short time scale monitoring. So if the time scale of the change is long, the thing that's causing it must be big and or far away. But if the time scales on which we are seeing changes are small, it must be close in to the star. And that's the key that we're using. We're going to, in the end, be able to provide constraints on how the star, the envelope, and the disk all interact through accretion flows. We're going to try to figure out what is physically causing these in all of these cases, try to interpret these light curves and tie them to physical models. We're going to get a whole bunch of rotation periods. We're going to be able to specifically study the variability properties of the most embedded objects, the class 1s, and to some extent the class 0s in these clusters that you really can't do from the ground because they're not visible in visible wavelengths. We're going to be able to constrain the long-term variability of young stars by comparing the cryogenic era to the post-cryo observations. We're going to find new eclipsing binaries, which are very interesting for a completely different reason. That's an entirely separate talk, but in summary, it anchors models of young star evolution. And we can also look for outflows and jets and brown dwarfs in the summed-up images that we have. So focusing on those as our three primary goals, let's look specifically at this first one because this is really the kicker. Because these are objects that we can never, at least in my lifetime, directly image. They're among the closest star-forming regions we know of, but still really insanely far away if you want to try to resolve the disk given current technology. So if we can watch the changes of these things with time, we can infer structure near the star, which is really the key. Okay. Over the shortest timescale changes, like I said, you're looking at small things that are near the star, and long timescale changes are big things further away from the star. In the infrared, you can see in much closer to the star than you can in the optical, but you do have to worry about what contribution is coming from the disk. So this image, I think I also showed you, this is a radio image of a young star that's in Taurus, which is only 140 parsecs away. The disk that you see here is about 230 astronomical units across, which is more than twice the size of the solar system. That inner ring there is 10 AU across, radius rather, and so that's about the orbit of Saturn, so that's about a 30-year period. And when we do this YSOVAR observations, we're measuring fluctuations on minutes, hours, days, weeks, and months. So, and we're also working around young stars that are up to 7 times further away than this thing. So it's giving us insight on what's happening really close to the star. So we do seem to be gaining on it. We had a couple of papers that came out of the original big Orion maps. The NGC 2264 campaign I alluded to earlier. I'm going to have more slides on it in a second, but we had the really key here is that we have a huge amount of simultaneous data, space-based, ground-based. It's made a huge difference in the way that we can interpret the light curves. And so there's a whole bunch of papers on that, including one that was just recently accepted. I'm going to focus a little bit later on the bursters as well as the dippers because I think those are kind of the easiest to explain both in terms of light curve shape and in terms of the physical interpretation. Our general approach has been to acquire the light curves and then try to see how we're going to put things into bins. And this was a bottleneck for a very long time. I think we finally cracked it, helped substantially by Anne Marie Cody. After we've put them into bins, then we can look for correlations with other things we know about these young stars. For CephC, for our work, this is why we're doing our work. We have to be able to establish what the star and disk parameters are of these young stars in CephC for which we have light curves so that we can fit into this overall flow and try to understand and interpret what's going on with the light curves in CephC. So these are some of the light curves we have from Orion. The two channels from IRAC are the closed blue circles are 3.6 and the open circles are 4.5. There's brightness as a function of time. Here we have very slow changes. There's probably slow changes in mass accretion rate, maybe self-shadowing of the disk. This one, maybe so you see it's irregular. Maybe this is changes in the accretion geometry that we're seeing. Here we have overall sort of periodic, but then you have this right here. This is a flare that's gone off on this star. Here we have something that is periodic, but has got an overall trend to it. So it's not clear exactly what's going on there. Here we have something that really is strictly periodic. It's probably a spot on the star or a warp in the disk. Here it's also periodic, but it's not clear exactly why one channel is steeper than the other. It may actually be instrumental in the end. But the main conclusion is that more than half of the class 1s and 2s and a third of the class 3s are variable. So there's more when you start to include ground-based J-band or I-band monitoring. Here you have ones where the J has a similar shape, but a much larger amplitude. Here you have ones where J is a similar shape and asimilar amplitude. Here you have a case where J is smaller or not variable at all. Here you have, there's a very few in which you have a phase shift, where the optical and near-infrared peaks at a different time than the mid-infrared, which is telling us something about the physics of the system. This one doesn't look periodic, but it is. It's an old friend of mine. I had found this one for my thesis in Orion. It goes around in about a quarter of a day. It turns out to be an eclipsing binary, not a rotation period. So the dippers. These are stars with narrow flux dips. So it sort of fuzzes along and then dips, and then fuzzes along and then dips, and then fuzzes along and then dips. On timescales of days, and we usually see more than one over a 40-day window, and the prototype for this kind of object is AA Tau, which you note has a torus name, so it's not actually an NGC 2264, but AA Tau was the only one that had light curves that looked like this, so the prototype is AA Tau. For us, we require more than one dip, unless we know for sure that it's dipping because we have corroborating data at another band. We have to have optical or J-band, and it has to be deeper in optical or J-band by at least 50% than it is in IRAC bands. You have to have, in order to find it, a continuum that's flat enough that you can find the dip by eye. There are, in the end, 38 class 1 or 2 objects, which is about 3% of our sample, that are dippers. And we have interpreted this as structure in the disks, so like clouds or warps in the disk, rotating into and out of view, temporarily occulting the central object. So these are examples of them. Here's just one dip, but you see that the J and the I are much deeper than the IRAC. Here it's quasi-periodic, and again, the J and the I are much deeper than the IRAC bands. So this is a model. This is a model of a disk with no magnetic support. That's a model that does have magnetic support. So it lifts the disk up, and so if you end up with texture in that magnetically supported piece of the disk, you could have it intermittently rotating into and out of view. And it might actually look something more like that. So there are some questions here. In order to make this geometry work, you have to be viewing it at just the right inclination to make this work. And you have to have it's a relatively narrow range of inclinations to do this. So we expect that the alignment occurs just some of the time. It's pretty rare that it occurs just right. So the overall fraction, taking this into account, we find that it's likely 5% in Orion. But Corot, which is a European space mission in the optical that was looking for transits, but it could look at NGC 2264, they also identified these dippers, and they found an overall fraction of 30%, which is very peculiar. Why are they so different? Well, it could be that this, even though Orion and 2264 are thought to be about the same age, maybe they're not. Maybe we're seeing different ages of stars. Maybe the different wavelengths matter. Maybe the things that are easier to see in optical have less dust, and that's also playing into the age. Maybe it becomes easier to see the dips in the optical versus the infrared. It could be that we have different cadences that matter. So for YSOVAR, it's hours between observations, but for 2264 in Corot, it's minutes. Maybe that matters. Maybe what's going on, although we prefer that not be the case, is that different people have different definitions. And when you sit down to look at the light curves, you have differently calibrated eyeballs. And so you pick out different objects as being the dippers. So to try to answer that, we started something called the Coordinated Synoptic Investigation of NGC 2264, or CSI 2264. Note that we left room for spin-off series, CSI, maybe not New York and Miami, but CSI and other clusters. This was mostly for the month of December in 2011, we took over all the telescopes we could get our hands on. So we had Spitzer for 30 days at 3.5 and 4.5 microns. We had Corot for 40 days in the optical from space. We had Chandra, which observed for 3.5 days in the middle there, just in X-rays. We had MOST, which is an optical space-based observatory that monitored for 40 days. We had ground-based spectroscopy in the optical. We had ground-based monitoring from several different telescopes over 3 months in bands between U-band and K-band. So that means that we have high precision photometry, high resolution spectra on timescales from less than a minute to a month or more, which is spectacular. This is the only star-forming region that could be observed by Corot. The CSI 2264 had both Spitzer and Corot working for the entire campaign. This is an exceedingly rare event. There is not going to be any other data set like this. Even though K2 is working in the ecliptic plane, Spitzer can't observe those same fields for as long as K2 can observe it. So nothing else, even still on the books, just in the planning stages, can do this kind of observation of young stars to this precision. So this is a spectacular data set. So there's NGC 2264. The region over which we monitored is that larger region, and then we stared at those two fields, and Corot monitored that larger region. So we found dippers. Here, the black is optical, the red and the blue is the Spitzer, and sure enough, we've got dippers. And these are almost certainly disk blobs or warps. In fact, if you scale the Spitzer observations using, admittedly, a non-standard extinction law, but still scale it, they match up really, really well. It's completely consistent with dust moving through the field of view, temporarily occulting the central object. There's also things that are clearly not dust. Here, the Corot and Spitzer light curve's doing something totally, totally different. So what's going on to resolve that problem of, us in Orion saying 5% dippers and the other group in 2264 using Corot saying 30% dippers, this is what's going on. The wavelength and possibly the cadence, but primarily the wavelength, is contributing to that difference in numbers, because we would never in a million years, given that Spitzer light curve, put that in the dipper bin, but from the Corot light curve, that's a dipper. So this is the resolution to that problem. Now, stochastic accretors, otherwise known as bursters, are kind of upside down dippers. They fuzz along and spike, and fuzz along and spike, and fuzz along and spike, and fuzz along and spike. So they're kind of upside down dippers in that sense. You do need to have, we found, Corot data to find them. Spitzer data alone doesn't enable you to find them. We found 25 from the Corot campaigns that look like this. And again, we have to have a flat enough continuum that we can identify the burst peaks. You have to have high quality data, and you have to have at least 6 of these bursts in order for us to include them in this bin. They turn out also to have an ultraviolet excess, consistent with the model I showed you earlier, and H-alpha emission, just like the model I showed you earlier, both of which are suggesting high accretion. They also turn out to be all class 2s. Some of the stochastic accretors have really well correlated Corot and Spitzer. I mean, here you see the fuzz along and spike and fuzz along and spike, and Spitzer's tracking Corot really well. But then others don't. So this is telling us something about the system inclination. We haven't completely unpacked exactly what yet. It could be, in some of these cases, specifically these stochastic accretors, that what we're looking at is funnel flows. So here is a model from this paper here. You've got the disk here, and in this case you've got the rotation axis pointing this way, but then the magnetic axis is offset. And since this pole is closer to this side of the disk, you end up, it's easier to have the matter crawl up the field lines and crash on the star there. And similarly over here. So you end up with spots that are, instead of arcs, spots, the clear spots, as well as the columns themselves. And so probably what's going on in these bursters is you end up with those accretion columns rotating into and out of view, or some other instability, fluid instability, modulating that accretion rate from the inner disk. So in summary, young stars vary a lot at all wavelengths at any time scale. They vary. And when we looked in the infrared on timescales of hours to years, we can start to characterize the IR variability of these stars and these disks. I highlighted here just the dippers and the bursters, but we have a much bigger zoo of variability, a lot of which we understand and a lot of which we don't yet fully understand. We're still trying to figure out, looking for patterns, looking for structure in the light curves, and there will be more papers This is the list of references I put up earlier. So these were the early results in Orion, and these are all the results so far from the NGC 2264, CSI 2264 campaign. There are papers on the smaller clusters too. So I have a paper that's statistics on the ensemble. This is the big data paper we've been talking about. There are 12 planned subsidiary papers, one per cluster. So the one on 1688 is out, the one on IRAS 250 is out, the one on GGD 12 to 15 is out, the one on NGC 1333 is out. Now these are the ones we're still working on. MON R2, a lot of work has been done. There's a lot more work that needs to be done. Lynn Hillenbrand is leading that effort. She's got a lot of ancillary data that needs to be folded in there. Serpens Main is being worked on. Actually, I think I have these reversed. Serpens South is Scott Wolk et al. Serpens Main is Elaine Winston et al. They are both at the CFA in Cambridge, Massachusetts, and they are working together to try to untangle these really rich fields. Serpens is in the galactic plane, and so the source density is really high, and so they're working really hard to try to sort out what's real and what's not in the light curves, as well as create a really good baseline catalog, which is what we're going to be doing in CephC. AFGL 490 is being worked on by Moritz Günther, and CephC is what we're going to be working on. So the main time series paper is probably still going to be Covey et al. I don't know if what we should do is write a separate paper just on the YSO selection or fold it in there. We'll see how this evolves. But we're going to be working on this cluster to try to create the good master set of YSOs in this region. IC 1396A, there's a huge amount of data, cryo monitoring, post-cryo monitoring, just an insane amount of data that I still need to work on there. And NGC 2264, there's been a lot of work just on the class 2s that have corot data. There has not been really any work on things that only have infrared light curves, and there's a lot. And I did a lot of work on this last summer, spring and summer, and then a more urgent project pulled me away. So I will get back to this, and then someone's going to have to pick up Orion again and do a final analysis. This is an enormous field. It's going to be months and months of work, and so it's probably last on the list. So hopefully that provides sort of an overview of what we have and where we're going.